Welcome to the multivariable calculus section. In this section we'll be discussing vector functions and space curves. So now that we have a general sense of the equation of a line, let's delve into the application of said equation. So back in algebra, we can recall the equation of a line is f of x is equal to mx plus b, or y equals mx plus b. Now, comprised of both a y component and an x component, the two-dimensional equation of a line encompasses the regarding of an xy coordinate plane. Now, in multivariable calculus, we will be dealing with a three-dimensional equation, which is a vector function, which encompasses the coordinates that make up an xyz plane. Therefore, our equation of a vector function is as follows. We can say that the vector r, or our vector function, is equal to f of t, g of t, h of t. So, as you can see here in our graph on the right, we have a vector function. Now, a vector function is comprised of a point and a direction, similar to all lines. So that means that this vector function, we have our point 3, negative 1, 7, and our direction is going to be negative 3, 7, and 2. So what this entails is that our vector function is going to look as follows. 3, negative 1, 7, plus t, negative 3, 7, 2. Now, that is our vector function for the following function, or line, as we can say. Now, over here we have a cyclical graph that's in 3 dimensions, and it does not lie on the xy plane. So we know that a parametric curve would lie on the xy plane. In calculus 2 we learned, but it would not occupy a space. We can say that this space is 1. Now, if we wanted to map this out, we could say that our vector function is equal to cosine t, sine t, and 1, because it's occupying 1 and in space. And that would give us our equation of a parametric curve, or a parametric vector function. Now here we have this seemingly cyclical but also linear, you can see that it's either scaling upward or scaling downward type of vector function. Now this is what we call a space curve. So this can be modeled when we parameterize our z function. So in the previous one we had our z equal to 1 because it occupied a point in space. But now we can say that if our vector function is equal to cosine t, sine t, and t, we're saying that as this function progresses, it's going to continuously increase its space in the z-axis, whereas this point would always occupy the 1 value in the z-axis. So that's a little insight on how vector functions and space curves works. I hope that helps, and there's a bunch of problems and additional assistance on the website. Thank you.